Hello students, in this video we'll discuss the idea of dimension of a subspace of Euclidean space. Let's let V be a subspace of Euclidean space. Okay, just maybe we can just take Rn for example. Okay, and what I want to say is suppose that V is the span of a collection, let's say V1 up to Vn, or maybe we can call that Vm, for example. All right, so V is the span of these vectors over here. Moreover, suppose and V contains a linearly independent set let's call these things U1 up to UK, like that. It contains K of these vectors. Then it has to be the case that K is less than or equal to M. Then K is less than or equal to M, okay? And this is going to be the basis of our idea behind subspaces, because of dimension of subspaces, because I want to I want to show that basis has the same cardinality independent of which basis I select, okay? And so this is going to be the key to this argument over here, because remember that bases have two things, they're linear independent and they span, okay? So that's the first step in our procedure, okay? So how do we prove this over here? So the proof goes as follows. So proof of this fact, well, I know that to be linearly independent, this set cannot contain any zeros. So note, none of the UI are 0. If they were, then the set would be independent. Then the set would be dependent. Okay? So in particular, what that tells me is the following. It tells me that U1 is equal to a linear combination of these Vm, right? It'd be lambda 1 V1 plus all the way down to lambda m Vm, where not all the lambdas are equal to 0, right? So not all. Okay. Because U1 is not equal to 0. So without loss of generality, assume that lambda 1 is not equal to 0. So by rearranging, assume that lambda 1 is not equal to 0, okay? So I just permute the indices to do this, okay? And then what I can do is if that's not equal to 0, then we can write V1, then V1 is in the span, by throwing the U1 on the other side, is in the span of U1, V2, up to Vm. So what I've done over here is I've exchanged one of the U's for one of the V's, right? So that's the exchange of a U for a V. And that's the key behind this argument over here. So we've exchanged a U for a V. Okay, great. And now let's suppose, by way of contradiction, suppose if what? If K was bigger than M, we could exchange the first M of these V's, every Vm, Vi, I between 1 and M, for Ui. Okay? And so what that would tell me is that would say that my Um, so hence what would we be able to say? We'd say therefore that then, since K is bigger than M, that would say that U of M plus 1, which definitely exists because K is bigger than M, would be in the what? Would be in the span of U1 through Um, and that would contradict the independence. Contradicting the independence. Okay, so that proves our result, right? Great. And so now what we can do is we can state the following. Now suppose now, proposition, suppose that V1, Vk, and U1 through Um are bases for V, which is a subset of Rn, a subspace. Okay? Then K is equal to M. Okay? And so how does the proof of this proposition go? The proof goes as follows. We can use two representations. I know that V is the span of V1 through Vk. And it's also equal to the span of U1 through Um. And this set is independent. So this set over here is linearly independent. And this set over here is linearly independent. So in other words, what this tells me is that first proposition over here, which is proved over here, this is going to tell me what? This is going to tell me that K, the span over here, so there's the M, the spanning has to be bigger. So this over here tells me that M, this is linearly independent, and is a subset of V. M is going to be less than or equal to K. And this over here tells me that K is going to be less than or equal to M by our previous proposition. So that K has to be equal to M. So K is equal to M. And so that gives us our definition of what a basis is, right? So now we can formally say, so if I give you any two bases of a subspace of Rn, those bases need to come, those bases have to have the same number, the same cardinality of vectors in a spanning set, right? So here's a definition. So definition, the dimension of a subspace V, subset of Rn, is the cardinality of a basis. Okay, excellent. And of course we know this is invariant by this proposition over here. This is invariant by the proposition. And of course, one thing that we'd automatically get for free is with this beautiful result that we know that since E1 hat up to En hat is trivially a basis, we can conclude from this that the dimension of Rn is exactly equal to n. So I've constructed a notion of dimension which is consistent with the idea that n-dimensional Euclidean space is in fact n-dimensional, right? And so we're going to use this criterion that once I find a basis for a subspace, I'll look at the cardinality of that one given basis. Since the cardinality is invariant independent of bases, I can say that that invariant will define my notion of dimension of a subspace. Thank you very much.